Hey, congratulations and welcome to Chapter 3. Chapter 3 is about linear equations and linear inequalities. You can see we've got 8 lessons in here. The first one is about graphing linear patterns. But let's take a look here at the chapter opener. The chapter opener discusses Stephen's coin collection, and it describes for you how he collects coins. From that description, we can create a set of descriptors, if you will, that will tell us what is going on with his collection. The first one is an equation. That equation shows us that the total number of coins he has is equal to the 25 he started with plus the 10 per week that he gets times the number of weeks he's been getting them. That'll give us the total number that he has if we know however many weeks it is. The second form is the arithmetic form of presentation of data. And in that one we have a table where we have W, which is weeks, T, which is total number of coins. And as the weeks go by, he gets more and more coins, and we can see that in that tabular form. In the last one, this is the geometric form of the presentation, and this is a graph, which is a geometric construct. And in this graph, we have some dots, some data points that are ordered pairs that show us how many coins Stephen has in any given week. You'll notice that the dots are not connected. And the reason they're not connected is because of how he gets coins and the unlikelihood that he might get a fractional coin of any type. By just putting the points, we're saying this is discrete data. Discrete is D-I-S-C-R-E-E-T, discrete, which means it's just simply the data points themselves, no line connecting them, because this is what in fact is happening week after week with Stephen's collection. The table is in ordered pairs, as I said. They will make the equation true, and it gives us a way to plot it. So here we've seen 3 quick ways to look at a linear equation and evaluate it and see what kind of results it might have. One is with an equation, the 2 is the arithmetic method with a table, and number 3 is the geometric method using a graph. Okay, we're heading into 3-1. The assignment, as usual, is to do the covering the ideas and applying the math. Remember to graph neatly and accurately. Use a ruler to draw your lines and have some fun with it. In this graphing linear patterns, we've got a number of ideas in it. The first one under the big idea is this idea of constant increase and constant decrease situations. These kind of situations lead to a linear equation. There's a couple of discussions in here about it that you should read through this. Of course, you should have read it. You should have made note of the vocabulary and what they're being asked. They're asking you to remember there. If we look at example 1, and I'll go through another alternative example later, it shows us a flash flood situation where the water has risen up. Well, after a flash flood, it stops raining and the water levels start to drop down to their normal level. Well, what kind of situation would this be? This would be a constant decrease situation where there is a rate of change in how fast it's changing per hour. And you'll notice they've represented that. It was 54 inches above normal, and it was dropping at a rate of 1.5 inches per hour. And so what we do in this relationship is we have y, which is the height of the water, is equal to 54, which is what it started at the beginning of time. This would be at time 0, or when x is 0, y would equal 54. Then as each hour passes by, we have a drop in the water, so we're subtracting the decrease, minus 1.5 times x from 54. we can look at the lake level at various times. We would find that we could create a table for it, and I highly recommend making a table no matter what you're going to do. And that table shows us that we have the time in 0, 1, 2, 3, 4. We have the height, and in this case it shows the equation and it being solved for. So I have my x value and my y value, and in the third column they show it as an ordered pair. So ordered pair, which is x, y with parentheses around it, comma in between, and they're going to plot this information on this graph. Some things to note about this graph is there are the points that they plotted for 0, 1, 2, 3, and 4 hours. They've connected the line in between them because it wasn't a step. It didn't just go from 54 to 52 and a half. Over the course of the hour, it was dropping in a steady linear fashion. The other thing to note is this little squiggle in the graph. That's right here close to the origin. And that's a discontinuity. That means they jumped from 0 to 48 without putting all the data points in between, because that's really what we were interested in. We don't want to see it graphed across that. So once you go beyond that, if I were to extend this line down here, it wouldn't make a lot of sense because I don't know what happened in there. This would tell me that it's decreasing at this rate of half an inch. Excuse me, how many inches? Oh yeah, 1.5 inches, sorry. 1.5 inches every hour, and so this would continue down at 1.5, 1.5, 1.5, and onward. But this is just a shortcut to allow you to make your graph more compact. So we've got our line, and the domain here for x is that it's greater than or equal to 0, which point, the beginning of time on out. The range for y depends on for how long the level is dropping and when it gets back to normal. So that's our first example in here. In example 2, we have this example of the water level continues to drop, and it's asking how long will it take for the water level to fall to 3 feet above normal. Well, we need to first understand what is normal for this. And so look at the graph from example 1. The level of the water above the normal level is given by y. Find the point for 3 feet or 36 inches on the y-axis. The x-coordinate of this is 12, and this is shown by the arrows in the graph. The water level will be 3 feet above normal after 12 hours. So if we had extended this graph to be more like this one, again they have a discontinuity here, we could use this graph to help us predict that information. The last part of this is an activity. It's making use of an instrument that'll hook on to one of the TI calculators. It's an ultrasonic device that allows you to measure time and distance and have that information put onto your calculator. When you're ready to do this, come and see me or perhaps Miss Jennifer to get the device, and then look for the tutorial on how to do this. That'll be an addition to the 3-1 lesson. Once you're done with that, remember covering the ideas, applying the math, turn it in, mastery quiz, move on. Best of luck. Bring your questions in, talk to your friends, see what they got in mind for you. Have some fun with this. Okay, well, we'll go through another example here for 3-1. And in this example, it's a constant increase situation, right? It started off with 1 foot of water in the pool, and we want to fill it, and we're adding water to it, so it's a constant increase. And this idea of constancy is assumed to be true until we're shown perhaps that it's not. But we'll look at this problem. Sharon bought a new home with a 5-foot deep pool in the backyard. The pool had 1 foot of water in it. When she began filling the pool, Sharon noticed the water level rose 4 inches every hour. X is going to equal the number of hours since she began filling the pool, and Y will equal the depth of the pool in inches. We can model this situation with an equation, and then we can graph the relationship. The first thing to point out to you is that part of your information is in feet, and part of it is in inches. You're being asked to present your data in inches, so you'll need to do a conversion in order to make that happen. Before we make our table, though, let's see if we can create an equation to model this situation. We know that when the time started, there was 1 foot of water in the pool. So let's take a look at how we might go ahead and model this situation. And so we had 1 foot of water. So let's see, we got that. We got one foot. We know that the rate of increase is 4 inches per hour. So this is 4 inches per hour. And that should be enough to tell me how much is in the pool at any given time if I know hours. I need to convert this. This has got to be converted to inches. So we'll make that 12 inches. Okay, so I've got some information, and I know that X is the number of hours and Y is the depth. So Y is going to equal the number of hours, X, times the rate, 4 inches per hour, times X hours, plus we started with 12 inches. Now, does this work out? When we started, when time was 0, she hadn't started filling the pool yet, how much water was in the pool? Well, 1 foot, or 12 inches, same thing. So when X is 0, 0 times 4 is 0, we're left with 12. So we've got now an expression, an equation, that describes the behavior. You'll also notice that I put units in here because the units will cancel out if I've done this correctly. Hours cancels hours because hours over hours is equivalent to 1, right? Something over itself is a 1, so hours over hours is just a 1. I'm left with inches, so that gives me the right units that I need. All right, so we've got an expression. Let's go ahead and look at how we might make a table for this. And we're going to have this kind of what I call a t-table. Whenever you're graphing an equation, make a t-table. You only need a few points in order to be able to draw a continuous line. You need more points if it's going to be discrete and you want more information from it. But with this table, we should be able to get some information that will allow us to then graph the information here. So I'm going to make this as X, this is Y, and when X is 0, Y is 12 inches. When X is 1, might as well keep it simple. 1 times 4 is 4, 4 plus 12 would be 16 inches. And let's just get another point, so we're a little bit further away here, so we'll do a 2. And 2 times 4 is 8, 8 plus 12 is 20 inches. So we've got this information now. We could perhaps go and okay, we're going to go ahead and label this thing. we've got our x-axis down here. That's in hours. My y-axis is here. That's in inches. And we can see from this, we're going to go ahead and graph it. I got 0 and 12, and this is 1, 2, 3. So I'm going by ones, and I'm going to go here on the x-axis. We'll open this up a little bit. We'll make this a 1, this a 2, 3, 4. I need a little bit more room to work with. So at time 0, I was at 12. So I have a point right here. And in times, let's see, in time 1 I'm at 16, and so I have a point here. And in 2 hours I'm at 20. I'm all the way up here. And now I've got something that could be graphed. I don't have anything here in quadrant 2, because I'm not going to have any negative x values. I'm not going to have negative y values. Everything's going to be in quadrant 1. So I can go ahead and start here at this point. And we're going to make a line that's going to go up through those. And that's the line that's going to be our line of results, showing us what's going to happen for this particular body of work. Now, for the next part of this, going to have to kind of go back and clear a few things out. So let me go ahead and do that, and then we'll continue on. Okay, I'm going to redo this in a moment, but let's take a look at our next question. We were able to do the initial graph, but now I have a more pointed question, which is, in how many hours, if the water level continues to rise at the same rate, in how many hours will it take for the pool to reach a depth of 5 feet? Well, my previous scale only went up to 20 inches. And, well, 5 feet, that's a little bit more than 20 inches, right? It's 12 inches per foot. 5 times 12 would be 60 inches, would be 5 feet. So I would need to redo this graph, or I have to adjust the scale. Now, we had a fairly slick attribute we used, which was this little dashed line. Well, I could do something like that and see if I could get it, or perhaps I could go up and just change my increments to units of 4. Now, I suspect I'm going to be okay here in my x direction, but we'll see as we begin to do this. So what I want to know is how long, how many hours when it's at 5 feet, and I want to be able to get that from the graph. Well, I know that my starting point for this graph is going to be 12. So I'm going to put in my little break right there, and we'll go ahead and we'll make this 12. And then this will be 16, 20. So I'm going up by 4s. So this first unit was we jumped to 12, and then we went up after that by 4s. So that would be 24, 28, 32, 34, 36, 40, 44, and I'm just kind of put a little gap as I'm writing this in. So 44, 48, 52, let's see, so 60 is going to be here. And then this will be my hours. So I went by twos, but I think I'm going to go by ones. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so I've got a pretty good range of data points here, and this is my time in hours. Again, I know that it was 0. At 0 it was 12 inches, and at one hour it was 16 inches, and at 2 hours it was 20 inches. So I can go ahead, I'm going to draw my line. And from this begin to predict something. So at 60 inches I come across and I intersect the line here at this point right in here. So this point right there, and I'll drop down here and I'm at 12. So it would appear the answer to my question, which was how many, if the water level continues to go up, how much will the pool reach? How long will it take for it to reach to 5 feet? Well, it gets to 5 feet in 12 hours, so my answer is 12 feet 12 hours for 5 feet. And I could just pull that directly off of the graph. So that's it for the examples in here. You got a lot of others to work on. Again, be careful with your graphs. If, like I did, if you didn't get it right to begin with, redo your graph. Don't just try to force it. Work to try to make it make sense and work out. Covering the reading, applying the math, looking for you on the mastery quiz. Good luck with that. See you soon.